In the simplest sense, a force is a push or a pull. A mutual action is an interaction between one thing and another. When you push on the wall pushes on you. The interaction that drives the nail is the same as the one that stops the hammer. A hammer exerts a force on the nail and drives it into a board. There also has to be a force exerted on the hammer to stop it. Newton reasoned that while the hammer exerts a force on the nail exerts a force on the hammer. In the interaction, there are a pair of forces, one acting on the nail and the other acting on the hammer. Newton's third law describes the relationship between two forces in an interaction. One force is called the action force. The other force is called the reaction force. Neither force exists without the other. They're equal in strength and opposite in direction. They occur at the same time. Newton's third law is often stated, for every action, there's an equal and opposite reaction. In every interaction, the forces always occur in pairs. You push against the floor, and the floor pushes against you. The tires of a car interact with the road to produce the car's motion. The tires push against the road, and the road pushes back on the tires. When swimming, you push the water backward, and the water pushes you forward. The interactions in these examples depend on friction. A person trying to walk on ice where friction is minimal may not be able to exert an action force against the ice. Without the action force, there can't be a reaction force, and so there's no resulting forward motion. When the girl jumps to shore, the boat moves backward. There's a simple recipe for identifying action-reaction forces. First, identify the interaction. Let's say one object, A, interacts with another object, B. The action and reaction forces are stated this way. Action. Object A exerts a force on object B. Reaction. Object B exerts a force on object A in the opposite direction. It doesn't matter which force we call action and which we call reaction. Sometimes the identity of the pair of action and reaction forces in an interaction isn't immediately obvious. For example, what are the action and reaction forces in the case of a falling boulder? If we call the action Earth pulls down on the boulder, then the reaction is the boulder pulls up on Earth. When action is A exerts force on B, the reaction is simply B exerts force on A. Earth is pulled up by the boulder with just as much force as the boulder is pulled down by Earth. The forces are equal in strength and opposite in direction. The boulder falls to Earth and Earth falls to the boulder, but the distance Earth falls is much less. Although the pair of forces between the boulder and the Earth are the same, the masses aren't even close. According to Newton's second law, acceleration is not only proportional to the net force, but it's also inversely proportional to the mass. Because Earth has a huge mass, we don't sense its infinitesimally small acceleration. When a cannon's fired, there's an interaction between the cannon and the cannonball. The force the cannon exerts on the cannonball is exactly equal and opposite to the force the cannonball exerts on the cannon. You might expect the cannon to kick more than it does. The cannonball undergoes much more acceleration than the cannon because its mass is much smaller. F represents both the action and reaction forces, big M the mass of the cannon and little m the mass of the cannonball. Do you see why the change in velocity of the cannonball is greater compared with the change in velocity of the cannon? We can extend the basic idea of a cannon recoiling from the cannonball it launches to understand rocket propulsion. The balloon recoils from the escaping air and climbs upward. If a balloon is released and allowed to move, it accelerates as the air comes out. A rocket accelerates in much the same way. It continually recoils from the exhaust gases ejected from its engine. Each molecule of exhaust gas acts like a tiny molecular cannonball shot downward from the rocket. Both the rocket and recoiling cannon accelerate because of the reaction forces created by the cannonballs they fire. Using Newton's third law, we can understand how a helicopter gets its lifting force. The whirling blades force air particles downward, action. The air forces the blades upward. Reaction. This upward reaction force is called lift. When lift equals the weight of the craft, the helicopter hovers in midair. When lift is greater, the helicopter climbs upward. Birds and airplanes also fly because of action and reaction forces. When a bird is soaring, the shape of its wings deflects air downward. The air in turn pushes the bird upward. The slightly tilted wings of an airplane also deflect oncoming air downward and produce lift.